So now we are going to discuss this theory of P series. As an example, this comes very often. Unlike the other tests we are talking about, uh, here we can definitively say what is happening to this kind of series. So this P series is nothing but 1 by n power p. By default, I say n equal to 1 to infinity. Let's say this is called as a P series, also called as the harmonic series. So this is one where Euler famously also proved that the um, number of primes is infinite by taking this series, like summation 1 by n is 1 plus 1 by 2 plus 1 by 3, so on. This surprisingly diverges. So we can show, I mean, by this theory, this is what I would like to explain. Similarly, if take it as 1 by n square, 1 by 1 square plus 2 square, 1 by 3 square, and so on. This is for p equal to 2, right? So we will state this theorem, which eventually shows that this diverges and this converges. So the theorem is as follows. The series summation 1 by n power p is one convergent if whenever p is greater than 1, right? So that's the case in the second example I gave, and it diverges if p is less than or equal to 1. Remember, it's p is lying between 0 to infinity. So we have these cases, like you have one, either p is lying in this, it's exactly 1, or it's greater than 1. These are the cases. So let's look at this one by one. So this is the theorem about P series, and let me quickly give a proof about this. So let's, as I said, let's look at case by case. Case 1, I'm looking at p greater than 1. So let's first look at 1 by 1 power p, which is the first term, is clearly 1. Look at the terms 1 by 2 power p plus 1 by 3 power p. I'm note that I'm actually trying to club these terms, and this is going to be less than 1 by 2 power p plus 1 by 2 power p, because I've replaced 1 by 3 power p by 1 by 2 power p in the right hand side. So by comparing with a corresponding series, we are going to come to a conclusion. So then look at the next three terms. By the way, let's look at this. What happens here is 2 by 2 power p minus p, 2 by 2 power p, which can be written as 1 by 2 power p minus 1. So we identified what this bracketed term is. Now we'll look at another bracket, namely the next four terms. 1 by 4 power p plus 1 by 5 power p plus 1 by 6 power p plus 1 by 7 power p. These are the next four terms which I'm going to conveniently bracket it. So this strategy of uh, converting the given series into these bracketed terms helps us to identify what exactly is happening. So this is less than 1 by 4 power p. I retain the first term as it is, but the second term I replace by 1 by 4 power p itself. So remember what I'm doing? I'm replacing this term, and this term by 1 by 4 power p. And therefore, I have an inequality that my LHS is less than the RHS because the denominators are smaller. See, 5 is replaced by 4, 6 is replaced by 4, 7 is replaced by 4. But this right hand side turns out to be 4 times 4 by power p, which is 2 square by 2 power p the whole square, 2 square p. So which is uh, 1 by 2 power p minus 1 the whole square. Let's show with the pen. Okay, whole square. Okay, similarly, one can say that. Okay, now I will put down the whole series. My summation 1 by n power 1 by n power p for p greater than 1 looks like 1 plus 1 by 2 power p plus 1 by 3 power p plus 1 by 4 power p plus 1 by 5 power p plus 1 by 6 power p plus 1 by 7 power p, so on. I just took so many terms to explain what is happening. So I would like to club these into a bracketed term, club these in a bracketed term, and you can easily guess what is my next bracket going to be. My next bracket is going to be 1 by 8 power p up to 1 by 15 power p, which are 8 terms. So 2 terms, 4 terms, 8 terms, and so on. So it's the number of terms itself is going like a geometric thing, but um, uh, you would have already guessed that I'm trying to compare it with a geometric series. So what happens is that this, as per my previous analysis, is less than. By the way, the first term I take as it is, but this bracketed term I compare with the right hand side 1 by 2 power p, which is 1 by 2 power p minus 1. Plus this I've identified it as 1 by 2 power p minus 1 the whole square. And you can guess, and one can rigorously show that the next bracketed term is going to be 1 by 2 power p minus 1 the whole cube, and so on. So the original series is being compared with another series, which is GP. This RHS is a geometric progression with P being known as a greater than 1 term. Therefore, what is the ratio? The common ratio here is 1 by 2 power p minus 1, right? And the initial term, let's say A, that's how we are use this notation right from our 11th standard. A is 1. So limit to infinity of a GP with initial, I will write the notation as GP with initial term A and our common ratio R is A by A minus R. Now in this case, it is 1 by 1 minus 2 power p minus 1, and therefore for any value p, this is going to be a definitive term. This is, and therefore it converges. Therefore, the p series converges. Now case 2. Case 2 is when P is equal to 1. And this is the very interesting case because it goes to the first example that I said, because 1 by 1 power n P, if P is equal to 1, is nothing but 1 by n power 1, is nothing but 1 by 1 plus 2 plus 1 by 3 plus 1 by 4, so on. Well, let's see what is happening here. I already stated in my introduction what is happening. Euler famously showed that this diverges. So how? Let's see this. So for this case, again, we'll do the bracketing operation. In this case, what I will do is the first bracket is just these two terms, which is 3 by 2. The second bracket is going to be, consider this is the first bracket. The second bracket is 1 by 3 plus 1 by 4. And I would say now in this case, I'm going to compare it with this term, 1 by 4 plus 1 by 4. So what did I do? I replaced 1 by 3 by 1 by 4, a smaller term. Therefore, the right hand side is bigger, left hand side is smaller. Right? So this is clearly 2 by 4, which is 1 by 4. 1 by 2. Sorry. Okay. Now I have taken care of the third and fourth term. Then fifth, sixth, seventh, eighth, I will write it as 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8. This is the next in the series. Next 4 terms can be compared with 1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8, which is 4 by 8, which is again 1 by 2. See, notice the way I'm clubbing, I get things like this. Sometimes this going to the next page is difficult, but anyway. So, my summation 1 by n is 1 by 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6. This is what I've done. You can easily guess that next I will take 1 by 7 plus 1 by 8 right up to what did I do? I think I made some mistake. I took 1 by 5. Yeah, let me write everything. 1 by 9 plus 1 by 10 plus 1 by 11 plus 1 by 12 plus 1 by 13 plus 1 by 14 plus, see how many times? 1, 2, 3, 4, 5, 6, 7, 8, 9. No. I think I did a mistake. Yeah, the mistake is this. So I should have started with 1 by 5, 1 by 6, 1 by 7, 1 by 8. Then I would have got everything correct. I should here start with, yeah. I apologize for the mistake. It is 1 by 9 plus 1 by 10 plus 1 by 11, 1 by 12, 1 by 13, 1 by 14, 1 by 15, 1 by 16. That's it. We don't need more terms. This is my next bracketed term. And this eventually next bracket turns out that it is 8 by 16. Next bracket is less than 8 by 16 is 1 by 2 again. and so on. So you see, this can be written as the first, you can ignore the first term, but ignoring the first term, the rest all are like 1 by 2 plus 1 by 2 plus 1 by 2 and so on. Right? I think I should not be lopsided on this. It's not equal to now because I'm replacing them by corresponding numbers 1 by 16, 1 by 16. So I should say less than this. Okay, although the first term is taken as it is, but the other terms are taken in comparison with the right hand sides. So this I replace by 1 by 8, 1 by 8, 1 by 8, 1 by 8. This I replace by 1 by 16, 1 by 16, 1 by 16, so on. And therefore, this is less than what we can say this kind of a series. A series 1 by 3, 3 by 2, and a constant series half, 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 half. And I have explained earlier that if you have constant terms in a sequence, that diverges. So this partial sum always diverges. So sequence of partial sum diverges. Therefore, summation 1 by n diverges. Because simply that the original series is less than something which is always already diverging. It is already diverging. And therefore, for the case p equal to 1, namely 1 by n, diverges. Right? Now, what we are left out, remember again the number line, I said this is 0, this is 1. So if p is lying between 0 to 1, I said it converges. P lying greater than 1 converges. Equal to 1 diverges. What about case 3? P less than 1. We'll look at this. Case 3, P less than 1. Now, P less than 1 implies n power P less than n power 1. Implies 1 power n, 1 by n power P, I'm taking reciprocals, greater than 1 by n for all n. So whenever P is less than 1, 1 by n power P is greater than 1 by n. So what this implies? This implies in summation 1 by n power P, every term is greater than the corresponding term of 1 by n. Greater than corresponding term in summation 1 by n. Because I'm comparing this guy and this guy. Right? So by case 2, the RHS in this inequality, which I have not written in symbols, but in words I've written greater than corresponding terms in summation 1 by n. The RHS terms diverge. Therefore, the left-hand side, which is greater than the terms in the right-hand side, implies that LHS also diverges. Because we have a comparison that every term in my summation 1 by n power P is greater than the corresponding term in the summation 1 by n. This already diverges. And therefore, these terms should diverge because they are all greater positive terms. Hence, for this case, P less than 1, summation 1 by n power P diverges. Hence, we complete the theoretical part of P series. So I close the class here.